Hello everyone. Today I'm going to explain and discuss a new quantization technique released by Google called TurboQuant. And we will see how it is used by Google to compress the AI models, specifically the large language models, by up to six times. So we'll first look at the problem and then see how it solves that particular problem. So any AI model, specifically large language model, be it Gemini, Llama, OpenAI's GPT model that powers the Chat GPT, has something called the KV cache. So basically, what KV cache does, is it stores the mathematical outputs of the previous computations in a cache. Suppose you open a new Chat GPT window and you start talking with it, and as you keep the conversation going, it builds up the conversation, and to keep track of what was said previously, it maintains a mathematical cache in memory called the KV cache. Why is it mathematical? That because the k vector and the v vector are computed mathematically from the input prompts, and then they are cached. So the model itself is loaded into the memory. The memory requirements are for the model itself, the weights of the model, the large language model, because it needs space to load and to process the input and then give the output during inference. And on top of that memory requirement, there's another thing called the working memory, which is consumed by the KV cache, because it still needs memory to store all that cache of the from due to the previous conversation. So the KV cache poses additional overhead on top of the memory already consumed by the model weights. So just to give an example, let's say the model weights are 32-bit and the input context size is 128,000 tokens and 4096 dimensions for each layer. That gives us around 67 gigabyte per layer of KV cache that is maintained during the inference. It creates a huge bottleneck, it's slow, expensive, and it limits the context window. So how does Google exactly solve this problem? For that, we have to understand what the quantization is. Quantization is basically representing a number, a floating point number in a lower precision. So for example, to represent the full value of pi, 3.1459 and onwards, we need a 32-bit float. But if we are to round it off to the nearest integer, then it is 3. The 3 alone can be represented as a 3-bit integer. So for quantization, we need step size. The smaller the step size, the larger will be the quantization error. So basically, we are rounding off to the nearest step actually. So for example, let's say there are 2 bits. So for the 2 bits, the possible values, step size values are 4. So any number that is given in the weights has to be rounded to the nearest of the 4 steps that are selected. So if we select more bits, it will cause less error, but it will also cause more memory consumption. So that's the trade-off. So this is the quantization. So why does this overhead happen? So like two vectors can have very different scale. Now there's another problem. Sorry, I missed that. For to store the quantized weight, now remember, the quantization happens before inference. During the inference, the weights are reverted back to the original precision, which is the FP32, and then the inference is computed. So if we are quantizing a layer, we have to store the scaling constants as well, which is 1 to 2 extra bits overhead per block. Why does this overhead happen? Suppose that we have two vectors and both the vectors are of different size. The v1 is in decimals, small decimals, and v2 is large integers. For each vector we have for each vector, when we quantize it, we have to store the scaling factor separately alongside the vector itself. So to solve this problem of storing the extra scaling constant, Google introduced this TurboQuant. The TurboQuant basically quantizes the k part in the KV cache. The query vector is computed during the inference, so there is no need to cache that. Only the key vector, uh, which is the which has the most consumption out of the KV cache, the key vector is stored, because the key vector projection in memory is multiplied with because of the dot product with the query. The v vector is actually an addition in memory, so that doesn't create much of overhead. So quantizing the k vector gives lots of benefits in inference. So to eliminate the scaling overhead, the TurboQuant uses the polar quant first. So instead of quantizing in steps, uh, the vectors, and instead of quantizing in steps using the Cartesian coordinates, the vectors are quantized using the polar coordinates. So in polar coordinates, we compute the radius of two given points uh, in the manifold, which is square root of x squared plus y squared, and we need to calculate the angle of the vector compared to the reference axis, which is the theta is equal to arctan y over x. So the representation becomes the radius, the representation of a point in space becomes the radius and the angle. Now, we once we do that, we do not need to store, and this is done for every point, irrespective of their size, scale, and whatnot. So once this is done, the theta is always between 0 and 360 degrees Celsius. And here's the trick. So we don't need to save any overhead for the angles. Angles are the new quantized values that are stored when the k part in the KV cache is quantized. So the theta is always between 0 and 360 degrees. 360 degrees. Boundaries are mathematically guaranteed forever, no matter what layer, what block it is. Theta is always between 0 and 360. So if we were conventionally quantizing, it would be 3-bit values plus 1.5 bit overhead. That would be 4.5 bits in total. But we quantized the angles. It creates 0 overhead. So how does this work in, let's say, for a vector of 4096 dimensions? So we group the coordinates into pairs, x1, x2, and convert each pair to radius and angle, then recursively pair the radii and repeat. So for example, for point x1, x2, we compute the r1, r2, and then recursively repeat the same steps for the r1 and r2 itself to reduce the radii to just one final radius, and then we store the angles. The angles are then quantized individually based on the step size or number of bits of quantization used to quantize those angles. The final R is one parameter that needs to be stored in full precision, and that is per block. It doesn't create any overhead. Storing the angles, they need 0 overhead bits because angles are always between 0 and 360 degrees. And just to save the memory, they are quantized and then stored. Okay, so I will give a bit more details on how the step size is selected for the angles, but it's same concept as for quantizing any vector or any range of numbers. Now comes the next step. So when we quantize the angle, it introduces a bias into the quantized values, or rather it introduces an error in the quantized values, And when these quantized values are reverted back to the original points and the attention scores are calculated, it introduces a bias in those attention scores. Those attention scores are not the actual representation, or the not anywhere near the actual attention scores. The error is too considerable to introduce a bias in them. So as a step 2, QJL correction is applied. QJL is basically quantize Johnson Johnson-Lindenstrauss lemma. So Johnson-Lindenstrauss lemma says that basically if you have two vectors with 4 dimensions each, and you compute the dot product of both the vectors, multiplying each dimension respectively with the other in the second vector. Now, if these two vectors are reduced to just 2 dimensions, then the relative distances or the effective dot products remain the same. So if in other words, if a larger dimension vector is projected in a smaller dimension, the dot products, they remain consistent. So whatever the projections between dimension was here, it is preserved in the lower dimensions as well. Once we do this step, we to calculate this for the given key vector, we use a transformation matrix called S, which is normally distributed. Normal distribution is done to distribute the energy equally or normally along all the dimensions. And we multiply that with the k vector and only keep the sign bit. So idea here is again, now for each dimension goes down to 1 bit. So whatever the magnitude at each direction, at any dimension was, it goes down to a single bit, just the sign bit. Why? Because using the sign bit, we can estimate the actual score, the actual dot product score. It is, you can say, a symmetric estimate. The errors, let's say we have 4-dimension, two 4-dimension vector, and we take a dot product of both. So the error at each dimension, they are symmetric and they cancel out each other. So we have a very good estimate of the actual dot product. S matrix is regenerated from a fixed seed. It doesn't need to be saved in memory, which means it has 0 memory overhead. And the quantized, we only save the sign, and sign can be saved in a single bit per vector. Sorry, per dimension, which is not which is almost like 0 memory overhead. So the estimate become q dot k almost equal to pi over 2m into s dot q dot sine s dot k, and error shrinks to the order of 1 over m. Why does this trick work? As I said, geometrically, sine s dot k tells you which half space each projected component falls in. The dot product of the query projection with these signs is proportional to the cos angle between q and k, which is exactly what attention measures. So attention is not about the absolute scores of the dot product in the dimensions. It's about the relative difference. And sign bit, scores calculated using the sign bit can perfectly give us that relative difference between the dimensions. S is never stored. Both encoder and decoder in transformer can regenerate from the fixed seed, regenerate the S from the fixed seed. So what it can achieve is 6 times smaller KV cache, because K is drastically reduced in size. Speed up can also be achieved, like up to 8 times faster on H100 GPU if the matrix multiplication kernels are optimized for that specific hardware. And in accuracy, it has almost 0% loss across benchmarks and requires 0 retraining, and it is plug and play. So let's go to the benchmarks. that I computed. I will share this notebook publicly with this video. So I have done some benchmarks locally on my laptop, which is M4 Max MacBook with 48 gigabytes of shared memory or unified memory. So let's first look at some distinction between KV cache and model weights. TurboQuant basically compresses the KV cache. It doesn't do anything to the model weights themselves. It quantizes or compresses the working memory of the model. So why does KV cache matter? So for a given like a model, for example, Quant 3.5 with 4 billion parameters at 4K context, the KV cache is almost 1 gigabyte with half precision. And at 32,000 token context, the KV cache is around 8 gigabytes at half precision, and at 128,000 token context, the KV cache comes out to be, and this is for a 70 billion model, sorry. The KV cache for a 70 billion model at 128K context is almost like 40 plus gigabytes at half precision. So this is where TurboQuant actually shines. So there are two major steps. One is the polar quant, and second is the QJL error correction. The scores from both are added, and we have the final dot product score, which can be used for the attention itself. So these are the hardware specs of the machine I'm going to run the benchmarks on. I've already run all these cells, so we will go directly to the results. But first, let's have a review on how TurboQuant works. This is the original. This can be original K vector. We can see it has outliers. It has randomly distributed values. There's no clear distribution, data distribution that we can see. Another step that I forgot to mention before is that before applying the polar quant, to make it more meaningful, the energy for all the dimensions is distributed normally. Okay, so what it means is that instead of skewness in the vector, we distribute or the if the original vector is lopsided, we multiply it with the transformation matrix in such a way that the density or the energy or the values across the dimensions are normally distributed. Okay, what this helps us achieve is that it makes the polar quantization more purposeful, because then we will have normally distributed rotated vectors, each having a meaning in the overall contribution. So once we do this step, we calculate the angles, then we compute the centroids and approximate each angle to its nearest centroid, hence the quantization of the angles that is computed. If we select 2 bits, that are 4 centroids, so we have to round off each angle to its nearest centroid. This will introduce much error, which we will see later. The higher the bits, the less the error, but then this can increase the memory consumption. So if we use 2 bits per coordinate, the mean squared error goes high, and the cosine similarity is the lowest. But as we increase the bits per coordinate, we can see the cosine similarity in the final score for attention becomes higher, and the MSE decreases. So here we can summarize this. For 2 bits, MSE is highest, cosine similarity is lowest, but the compression is highest as well. You can achieve 8 times KV cache compression. Higher the bits, lower the MSE, higher the cosine similarity, but then lower the compression as well. But this still is much better. Let's, for example, if we use 4 bits quantization to quantize the angles in TurboQuant, this achieves significant better results as shown in the benchmarks in the official paper compared to any other standard quantization technique used to quantize the KV cache. Okay, we proceed with loading the model. We will use Quant 3.5 4-bit, 4 billion parameters, 4-bit quantized. Its weights are 4-bit quantized. Its KV cache is loaded in the full precision. And then we will apply the TurboQuant on top of it. So we'll have a baseline, standard KV cache, no compression, 16 bits per element, already in the half precision. We'll apply the TurboQuant with 4-bit, 4-bit centroids, 4 bits per element. The expected compression is 4 times with 3-bit per centroid, which is as per the official paper of TurboQuant, it is the sweet spot, achieves 5.3 times the compression. And then we have the 2-bit, the lowest compression, the lowest quantization level, 2-bit centroid, only 4 centroids possible, 2 bits per element, and achieves the highest compression 8 times. Memory, theoretical KV cache size at various sequence lengths. Okay, these are the metrics we will be comparing: memory, speed, and quality. Okay, I'll fast forward this. Memory benchmarks. You can see at very long context length at 32,000 context length. FP16 for FP16 baseline. The memory is almost 1 gigabyte in KV cache alone. With TurboQuant 4-bit, this reduces to 260 megabytes. With 3-bit, 196 megabytes, and 2 bits, 132 megabytes. Drastic reduction. Almost similar to what was speculated earlier. And then, we can draw the comparison here. As the sequence length, the input context window increases, the KV cache size increases as well. We can see here, it goes up to 1 gigabyte on the unquantized KV cache using half precision FP16, but it's drastically reduced. The results can be seen here, with a 2-bit achieving 8 times compression. The speed benchmarks doesn't give us much significant result on this specific particular hardware, because the multiplication kernels are not implemented for MLX. MLX is the inference engine I'm using for Apple Silicon. So if it were NVIDIA hardware, we would use the Triton kernels with TurboQuant, and that would have given us much speed improvement. I don't know the numbers, but it's significantly high. We can see that it's actually reducing the speed, because it adds an overhead of computation when we revert the KV cache vector dimensions back to the original values from the polar coordinate and QGL approximations. The memory is like it's a somewhat reduction in the memory. But the most important point is the quality benchmark. The most important benchmark here, the most important metrics in this benchmark are the memory consumption due to quantized KV cache, and then the drop in quality or change in quality due to that. And we're fast forwarding to the results. We can see that we have the baseline perplexity. Perplexity is basically how difficult it is for the model to predict the next token. So on the baseline for FP16, we have 11.277 perplexity for Quant 3.54 billion 4-bit quantized model. We can see for if we use the TurboQuant 4-bit, it increases it slightly, very slight increase, almost like 0.5%. If we use 3-bit, still very slight increase, 2.75%. And if we use the lowest quantization, 2-bit quantization, it is above 12, which is like 9% increase in perplexity. Bear in mind, even if we use the 2-bit, the perplexity increase, it's still much lower than any other higher quantization value achieved using the standard quantization techniques. So these are much better results. So as I mentioned earlier, the 3-bit is sort of sweet spot. It still give us the perplexity increase lower than the industry thresholds, which is acceptable for the model performance. So for these benchmarks, we can see we had drastic memory reduction. The speed, we couldn't get any benefit for in speed because of the lack of multiplication kernels, uh, optimized multiplication kernels. But the quality, this is where we can see significant results, is that even using the lowest quantization, um, the perplexity increase isn't much compared to other quantization techniques. So if you use the 3-bit TurboQuant, which is the sweet spot, we can have very similar performance with very less drop in accuracy of the model. So that was the TurboQuant review. I hope this video was helpful, and yeah, I will see you guys again, hopefully. Goodbye.